Each workday, John, who lives in the Midwest, passes down a street lined with pin oaks as boulevard trees. Some are green and healthy, some others are a bit stunted and pale green, while still others are severely stunted with considerable dieback and yellow leaves. Currently, many have been removed. The leaves on the slide were plucked from those trees. What is the problem with these trees? A problem shared with many pin oaks planted in this Midwestern city. The problem is one of pH, a fundamental soil chemical that is the main topic of this video and a problem faced by many growers, landscapers, and gardeners around the nation. I'm Dr. DeBusk, and this video focuses on soil pH and how to manage it. Soil reaction describes acidity or alkalinity of a soil. Soil users are concerned about soil reaction because it strongly affects plant growth. Reaction is measured by the pH scale as shown in the figure, which gives sample pH values for common substances. The scale runs from a pH of 0 to a pH of 14. Readings between 0 and 7 are said to be acid. A pH of 1 is extremely acidic and a pH of 6 is slightly acidic. Examples of acid materials include vinegar, tomato juice, and lemon juice. These acid foods have a sour taste. Readings between 7 and 14 are alkaline or basic. The larger the number, the stronger the base. Soap is slightly basic, while household ammonia with a pH of 11 is strongly basic. Bases or alkaline substances taste bitter. The midpoint of the scale, pH 7, is a neutral point, which is neither acid nor base. Pure water, which has a neutral pH, can be a model in our discussion of pH. A very small number of water molecules break up to form a cation and an anion, as shown in reaction A. The cation in reaction is the hydrogen ion, H+. It makes a solution acid. The anion is the hydroxyl ion, OH-. It makes a solution basic. In pure water, the number of hydrogen ions equals the number of hydroxyl ions to maintain a balance. If pure water is exposed to air, carbon dioxide from the atmosphere dissolves in the water to form carbonic acid. Some portion of carbonic acid, a weak acid, quickly breaks down to liberate hydrogen ions as shown in reaction B. Now there is an excess of hydrogen ions, so this dilute solution is acidic. Water in equilibrium with air has a pH of about 5.6. In fact, rainfall itself is acidic even without air pollution that creates even lower pH acid rain. The pH scale indicates how acidic or basic a solution is by giving the concentration of hydrogen ions. The pH scale is a special scale for expressing hydrogen ion concentration as 1 over the log of the hydrogen ion concentration. The smaller the number on the pH scale, the stronger the acidity of a substance. Each pH point multiplies acidity by a factor of 10. A pH of 5.0 is 10 times more acid than a pH 6.0 and 100 times more acid than pH 7.0. The balance between hydrogen and hydroxyl ions dictates pH. Soil with far more hydrogen ions than hydroxyl ions is very acid. With only a few more hydrogen ions, it is slightly acid. On the basic or alkaline side of the scale, the reverse is true. Soil users more commonly find that soil ranges between pH values of 5.0 and 8.0. Soil pH results from the interaction of soil minerals, ions in solution, and cation exchange. In the simplest terms, high pH is caused by the reaction of water and basic compounds of calcium, magnesium, and sodium to form hydroxide ions. Very basic soils, pH greater than 8.0, are more than 100% base saturated. That is, not only are all exchange sites filled with base cations, but the soil contains free particles of mineral carbonates, CO3, such as calcium carbonate or lime. These are caused by calcareous soils. The pH of very alkaline soils results from reactions of carbonates with water to form hydroxyl ions, according to reactions C and D. Soils tend to be alkaline in climates where annual precipitation tends to be lower than annual evapotranspiration, generally where rainfall is less than 20 inches per year. Low pH is caused by the percolation of mildly acidic water, which neutralizes the bases and replaces the base cations on the cation exchange complex with hydrogen ions, as shown in reaction E. When pH declines to about 6.0, aluminum begins to leave the structure of silicate clays. Aluminum ions react in several steps with water to form hydrogen ions and aluminum hydroxide compounds. The reactions are summarized in reactions F and G. Aluminum hydrolysis can lower the soil pH to about 4.0. This is the most acidic the majority of upland soils become. Relatively young soils, those not exposed to long periods of weathering and leaching, share the pH of their parent materials. Acidic parent materials include granite, sandstone, and shale. These materials are common in New England, the Great Lakes, and the Appalachian states. The soils of many states, including many of the Great Plains and some near the Great Lakes, develop from calcareous parent materials like limestone. When young, these soils tend to be neutral or alkaline. The pH of older soils is controlled by the percolation or lack of percolation of acidic water, as shown in reaction H. Percolation of acidic water causes hydrogen ions to replace exchangeable bases on colloids. The calcium and magnesium thus replaced can leach away as seen in the top figure. Soil acidity is greatest where average annual precipitation is greater than the average annual evapotranspiration, so there is potential for leaching. Where there is a net evaporative loss, soils tend to be alkaline. Plants acidify soils in two additional ways. First, when roots take up cation nutrients such as potassium, they give back an equivalent number of hydrogen ions. Second, growers take calcium and magnesium with each crop harvested. For example, every ton of alfalfa hay is a loss from the soil of 30 pounds of calcium and 8 pounds of magnesium. Each atom of a basic cation removed in cropping is replaced by a hydrogen ion, speeding soil acidification. Nitrification also contributes hydrogen ions to the soil. When nitrifying bacteria oxidize ammonium ions, it results in hydrogen ions, as in reaction J. Some products of decay are weak organic acids, and soil organisms contribute weak organic acids to the soil as well. Each plant grows best in a specific pH range. The pH ranges for a selection of crops are shown in the table. Except at pH extremes, the actual number of hydrogen or hydroxyl ions does not seem to be the main factor in plant growth. Rather, several soil conditions related to pH are more important to plants. These include the effect of pH on nutrient availability, the buildup of toxic levels of aluminum and other metals, and the effects on soil microbes. Which factor has the greatest effect on limiting plant growth varies from soil to soil and from plant to plant. Many soil elements change form as a result of reactions in the soil. These reactions, controlled by pH, alter the solubility and therefore the availability of nutrients. A good example is phosphorus, which gets tied up with aluminum and iron at low pH, and with calcium at high pH. Therefore, phosphorus is most available to plants at near neutral pH. Soil pH affects nutrient and aluminum availability as shown on the left for mineral soils in temperate climates. The thicker the bar, the more available the nutrient. The bars are not to scale and their effect is more extreme than it appears here. Note that the major nutrients and molybdenum are most available at near neutral or higher pH soil. The other trace elements are more available in acid soil. Note that pH in the range of 6 to 7 is a good average level for all nutrients. This range is also the best pH range for most plants. The solubility of iron compounds depends on the pH. Iron sulfate dissolved in acidic water on the left, so the colored solution is clear. Iron compounds precipitated out when pH was raised, making the solution cloudy in the beaker on the right. Calcium and magnesium become unavailable at low pH, not so much from being tied up, but from simple loss from the soil. At low pH, aluminum and hydrogen will replace those cations on the cation exchange complex. They will then leach out of the soil. Therefore, treating strongly acidic soils must involve the addition of new calcium and magnesium through liming. Soils that cannot supply enough of a nutrient may actually contain the element, but the nutrients is tied up because of acid or alkaline soil. At low pH, particularly below 5.5, aluminum and manganese or even iron can reach toxic levels in the soil. Aluminum actually leaves the structure of clay minerals, reaches high concentrations in the soil solution, and occupies most of the cation exchange sites. Aluminum toxicity severely inhibits root growth, causing them to become short, stubby, and unbranched, especially in acidic subsoils, and restricts the uptake of calcium and magnesium. Manganese problems are less common but can be equally toxic under certain conditions. In the greenhouse, iron toxicity may occur in certain plants such as geraniums if the pH of the potting mix drops too low. Aluminum toxicity occurs primarily in mineral soils of warm, humid climates. Aluminum problems seldom appear in organic soils because these soils contain little aluminum. Low pH may also mobilize toxic heavy metals that might be in the soil, such as lead or cadmium, allowing them to be taken up by plants or move into water supplies. Acid rain accelerates the acidification of forest soils, which liberates toxic aluminum and induces calcium and magnesium shortages. Soil organisms grow best in near-neutral soil. In general, acid soil inhibits the growth of most organisms, especially bacteria and earthworms. Thus, acid soil slows many important activities carried on by soil microbes, including nitrogen fixation, nitrification, and organic matter decay. A pH between 6.5 and 7.3 is generally optimum for these beneficial activities. Liming is practiced by growers to counteract soil acidity, mostly in those parts of the country where soil acidification occurs naturally. Liming improves crop response to fertilizers by improving nutrient uptake, especially phosphorus, reducing aluminum toxicity, and promoting the activities of such desirable organisms as the rhizobia bacteria that fix nitrogen for legumes. We apply the term agricultural lime to ground limestone or other products made from limestone. Lime materials are carbonates, hydroxides, and oxides of calcium or magnesium. While lime contains calcium and calcium ions play a role in raising soil pH, calcium itself does not neutralize acidity. It is the carbonate or other base anion that neutralizes acidity when mixed into the soil. Common liming materials include calcitic limestone, dolomitic limestone, burned lime, and hydrated lime. Calcitic limestone is nearly pure calcite or calcium carbonate, while dolomitic limestone is a mixture of calcium carbonate and magnesium carbonate. Burned lime or quicklime is made by heating limestone. Because calcium oxide is lighter, has a lower molecular weight, a smaller weight of it has the same effect as a larger weight of ground limestone. Burned lime also reacts more quickly in the soil but costs more and is hard to handle. Hydrated lime, or slaked lime, is produced by adding water to burned lime. It is also fast-acting. Hydrated lime neutralizes soil acidity in a sequence of reactions. When calcium hydroxide dissolves, A, calcium replaces aluminum and hydrogen on cation exchange sites by mass action. B, aluminum is tied up by reacting with water to form insoluble aluminum hydroxide. C, hydrogen ions released by these reactions combine with hydroxyl ions from lime to form water. D, ground limestone neutralizes the soil acidity in the reactions shown. The cation exchange reactions are the same as in the top figure. Hydrogen ions react with carbonate, a base, ions to form unstable carbonic acid, which immediately breaks down to carbon dioxide and water. The speed of this overall process varies according to the type of material. Hydrated lime dissolves quickly in the soil and reacts quickly. Ground limestone, on the other hand, dissolves more slowly and takes more steps to neutralize acid. 4 factors tell the grower how much lime is required: present pH, desired pH, buffering capacity of the soil, and the liming material to be used. By testing present pH and by knowing the correct pH for a given plant, a grower or soil testing laboratory can determine how much this pH should change. For example, if alfalfa grows well at a pH of 6.5 and the present pH is 5.0, then pH must be raised 1.5 points. However, pH itself does not tell how much lime to apply because it measures only the hydrogen ions in solution, not potential acidity, hydrogen and aluminum, adsorbed on the colloids. Hydrogen ions in solution can be termed active acidity, while adsorbed hydrogen and aluminum is reserve acidity. Picture soil storing hydrogen and aluminum ions in a large bin. This is acidity stored on the cation exchange complex, or reserve acidity. Attached to the large bin is a small one. This is active acidity in the soil solution that actively affects plant growth. Soil pH depends on the equilibrium between the large and small bin. The bigger the large bin, the more acidity is available for the small bin, and so the lower the soil pH. pH measurements measure only concentration of active acidity in the small bin. If one adds enough lime to neutralize that acidity, hydrogen ions are quickly replaced from the large bin. Thus, soil resists a pH change so long as the large bin is well stocked with hydrogen ions. Resistance to a pH change is termed buffering, and the ability of a soil to do so is buffering capacity. The greater the buffering capacity of the soil, the more lime must be applied. Buffering capacity of a soil depends on the amount of clay in the soil, the type of clay, and the amount of humus, essentially the cation exchange capacity. The table shows the amount of limestone needed to raise pH in different soil textures. The lime requirement of an acid soil depends on both pH and buffering capacity. The total lime requirement can be measured directly by a buffer test, for example, measuring the reaction of a soil to pH 7.5 buffer solution. The test does not measure actual pH, it is a guide to the amount of lime needed to correct pH. The pH of a soil sample is first measured to see whether liming is needed. Let us say a soil sample has a pH of 5.5. The laboratory technician adds pH 7.5 buffer solution to the soil sample and measures pH of the new mixture as 6.2. This means that the acidity of the soil lowered pH of the buffer solution from 7.5 to 6.2. The pH of 6.2 is called the buffer index. Looking at a table of buffer indexes, the technician reads the amount of lime needed to raise soil pH to the correct value. In this example, the table suggests applying 4 tons of lime per acre of mineral soil to bring the pH to 6.5 to 7.0. The result from a buffer index table will be found on a soil test report. Buffer tests suggest lime needs on a soil based on an average calcitic limestone or on pure calcium carbonate. However, different lime products have different capacities to neutralize acidity. This capacity is called total neutralizing power, TNP, or calcium carbonate equivalent, CCE. CCE compares an agricultural lime to pure calcium carbonate or calcite. 2 factors affect the comparison: the chemical nature of the lime and its purity. 1 molecule of calcium carbonate and 1 molecule of calcium hydroxide each have the same neutralizing power, but the latter weighs less. Calcium carbonate has a molecular weight of 100 atomic mass units, while calcium hydroxide weighs 74. Translated into a weight of lime, 74 pounds of pure hydrated lime has the effect of 100 pounds of pure calcitic lime. Neutralizing power is expressed as a percent per weight material relative to pure calcite. In this case, the percent of calcium carbonate equivalent equals 100 grams divided by 74 times 100, which equals 135. For any pure liming material, then, the CCE is the molecular weight of the calcite divided by the molecular weight of the pure material in question, multiplied by 100 to convert to percent. The table gives the CCE of several types of lime materials. The second influence on neutralizing power is purity. For example, calcitic limestone is mostly calcite. However, it contains other materials like silt that have no effect on acidity. A ground limestone that is 90% pure is only 90% as active as pure calcite. Since calcite has a neutralizing power of 100, the power of the limestone would be 90. If a lime recommendation were based on 90% pure calcitic lime, and a grower plans to use a different form of lime, a conversion is needed. The bottom problem shows how much burned lime with a neutralizing power of 150 would replace 3 tons per acre of the calcitic lime. These 2 factors, CCE and purity, are usually combined into a single factor labeled CCE or purity. The fineness of ground lime affects how rapidly lime acts. The finer the grind, the smaller the particle, and the greater the surface area in a ton of lime. Smaller particles expose more surface area to the soil solution and react more quickly. Thus, finer lime particles are more reactive than coarser ones. It takes less of a finer grind to achieve a given pH rise in a reasonable time than a coarser grind. While finely ground limes react rapidly and efficiently, they are used up rapidly as well. For a longer lasting effect, some coarse particles are useful. Most commercially available ag limes contain a range of size particles to ensure a rapid and prolonged effect. Particle size is measured by passing them through various sizes of wire mesh sieves, ranging from 8 mesh screens to 100 or higher mesh screens. The figure shows the efficiency of each particle size range. The effective neutralizing power is the final measure of how effective a lime product is at neutralizing acidity. EMP can be calculated as a percent of the effectiveness of pure calcium carbonate that is ground fine to be 100% effective. We calculate percent EMP for a particular lime product with the formula percent effective neutralizing power equals the percent calcium carbonate equivalent times the fineness index times the percent of dry matter. The EMP is often showed as a guaranteed analysis on the bag of lime. So how can you use this number? The bag of dolomite on the slide says that 1,743 pounds equal 2,000 pounds of standard liming material. Therefore, if a soil test report says that you need to apply 3,000 pounds of lime per acre, which is 1.5 tons, you would divide 3,000 pounds by 1,743 pounds per ton, equaling 1.72 tons of lime per acre. Best results are obtained from liming when there is close contact between the grains of lime and the soil. To achieve this, lime should be spread evenly over the field and then mixed well into the soil. Lime spreading trucks do a good job of spreading the material. While most lime is spread in a dry form, some is finely ground and mixed with water or a fertilizer solution and sprayed on the field. After lime is spread, plowing and/or disking mixes the lime into the soil. In established pasture or other situations where plowing is not possible, lime is spread evenly on the soil surface. If it is not mixed into the soil, the lime slowly moves into the soil. Growers may lime at any time that is convenient. Lime should not be applied with certain forms of nitrogen fertilizer because it can cause nitrogen losses. The most important consideration is reaction time because it takes a few months for lime to break down in the soil. If faster action is needed, the grower can use fluid lime, hydrated lime, or more finely ground lime grades. It is worth noting here that when pH is adjusted by liming, pH begins to return to its former level, since soil acidifying processes continue to operate after liming. Sometimes soil can be too basic for good plant growth. This may occur with acid-loving plants preferring a pH range from 4.0 to 5.5, such as blueberries or azaleas, in even slightly acid soils. These plants apparently have a high iron requirement that can be met only in soils acid enough for iron to be readily available. High pH primarily ties up micronutrients such as iron, manganese, zinc, and others, leading to micronutrient deficiencies. For planting a few acid-loving shrubs, landscapers often incorporate large amounts of sphagnum peat moss into the planting soil. However, as peat decays, its activity declines and pH will rise. Peat is also not a practical amendment for large areas. For longer-lasting pH reduction and for larger areas, sulfur is preferred. Once applied and mixed into the soil, as described earlier for lime, Thiobacillus bacteria alter sulfur to sulfuric acid. Sulfur is available in granular and powdered forms and as a flowable liquid. The powdered form acts most rapidly but is more difficult to handle. Granular sulfur, while slower acting, spreads much more easily with application equipment. The table suggests sulfur application rates. As with lime, finer textured soils and those with high organic matter content need more sulfur than sandier soils. Sulfur reacts slowly, so treat soils several months or at least several weeks before planting if possible. It should be incorporated into soil several inches for best results. A number of other chemicals also acidify the soil and are used much the same as sulfur. These include iron sulfate and aluminum sulfate. Iron sulfate acts faster than sulfur, but more is needed, a bit more than 6 times as much. Aluminum sulfate can turn hydrangea flowers blue since aluminum ions dissolve in flower cell sap and produces blue color. Acidifying fertilizers, those containing ammonium nitrogen, also lower soil pH. However, these cannot be employed for sharp, rapid drop in soil pH. The amount needed would cause fertilizer burn. Mulching with acidifying materials like pine needles may also delay a pH rise, though the effect is usually slight. Some individuals mistakenly apply gypsum in the hope of lowering soil pH. As a neutral salt, it does not do so. In conclusion, soil pH depends on the balance of hydrogen and hydroxyl ions in the soil solution. Changes in pH can often be achieved through application of lime or sulfur.